Alright, now we're going to solve problem 9.2, which requires us to pretty much do 9.1, but on a cold air standard basis. And we have to evaluate our specific heats at 300 K. Alright, so let's get started. So since we have to use our specific heats, let's just evaluate them right now. And they're being evaluated at 300 K, as stated in the problem. So our CP equals 1.005 kilojoules per kilogram K, and our CV equals 0.718 joules per kilogram times Kelvin. Alright, so our graph looks something like that. So the easiest way to solve this problem is to find the states, the temperature at each state. We already know that T1 is equal to 300 K, and this is isentropic from 1 to 2 and from 3 to 4. So we can use our isentropic equations to find our T2, which is going to be times our K. It's going to be this equation. Our K is going to be equal to 1.4 at 300 K. So, and we also are given that our compression ratio is equal to 9. So we have this, and we have this. So after we plug them in, we get 9 times 300, 1.4 minus 1. Our T2 is going to be equal to 0.5 K. Now that we found our T2, we can find our T3 using our energy balance equation. Let me just erase this. So our T2 we found to be equal to, so mass balance equation for state 3 equals M U3 minus U2. Our work, our heat addition, as our work, and this equals to 0. This whole mess is equal to CV T3 minus T2, and that's going to be equal to our Q23, which we already know to be 1350 kilojoules per kilogram. So we solve for T3, and that's going to be able to equal to 1350 over 0.718 plus our T2, and all that is going to be equal to 2,600 and 2.7. Alright, so let me add this right here. And erase this. Alright, now for T4 we can use the same process we did to find our T2, which is also isentropic. So T4 is equal to our P3 over P4 K minus 1 times T3. But you have to remember that that V3 over V4 is also equal to V2 over V1, which is our compression ratio of 9. I'm sorry, 1 over 9. So we've solved for T4, and that's going to be equal to 1 over 9, 1.4 minus 1, minus our T3, which is 6.2.7 K. Our T4 is going to be equal to 1080.8 Kelvin. So now that we have our T4, I'm just going to add it here, 1080.8, and then I'm going to erase the rest. So now we can get to part A of the problem, which asks what is a work net. So we know that a work net in a cycle is equal to a Q net, which is equal Q in minus Q out. We already know our Q in, and our Q out is going to be equal to U4 minus U1, which this equals, using our specific heats, T4 minus T1. Sorry, I went a little bit messy there. But this, I'm just going to go over here, is going to be 1350 minus CV, which is 0.718, times 8 minus 300. Sorry, it's a bit messy. So I'm just going to rewrite it again. $13.50 minus 0.718 times 1080.8 minus 300. Okay. After we solve this, we get that our work net is equal to 789.4 kilojoules per kilogram. And that is the answer to part A. For part B, we need to find our thermal efficiency, and that is going to be our work net over Qn, which is the value we just found, over Qn, which we were given, and that's going to be equal to 0.58, which is 58%. Now part C asks us to find our mean effective pressure, and for that I'm just going to erase the whole board. So we need to find our MEP, and that equals to our work cycle, which we already found, over displacement volume. So this equals work cycle over V1, V2 over V1. So in order to find V1, we use our PV equals MRT equals RT. And after solving that, we get that it's equal to 0.861 meters cubed per kilogram. So we just plug it back into the equation. We already know that V2 over V1 equals 1 over 9. So MEP is equal to our work that we found previously over our V1 times 1 minus 1 over 9. And then we have to play with our units. And after solving that, we get that our MEP is equal to 1031.4 kilopascal. And that solves all of problem 9.2.